Good morning, everybody. So we were talking about dynamic memory management at the end of the last lecture. So let me just go back to an example that we had. So in a previous example, we had a variable length array that was declared inside of a function, right, called makeArray. So makeArray makes an array, well, attempts to make an array and return a pointer to the first element of the array. The way that we implemented it was we created a little variable length array of the size requested by the caller, filled in the elements of the array, and then returned a pointer to the first element of the array, right? And we saw that when you run this program, it crashes when you try to run it, right? So when you try to print out, or when you try to access the elements of the array, it doesn't work, right? And remember, the reason that it doesn't work is because of that, right? When you make a variable length array or any fixed size array using a notation similar to that, you end up having an object that has automatic storage, right? The lifetime of ARR starts here and it ends there. So if you return a pointer to ARR or to the first element of ARR, that object no longer exists, right? So when you try to use the pointer ARR down here, right, and you pass it to another function that tries to access the elements of the array, that function now accesses memory that's no longer valid, and in this case, the program crashes. All right, so to get around that, to get around that problem, what you need to do is you need to create an object whose lifetime persists across multiple function calls. You want to be able to control the lifetime of the object, so now you're in the situation where you require dynamic memory management. Right. It's relatively straightforward, so mechanically it's easy to do. As the programmer, you have to remember that when you're done with the memory for that object, you have to free it. Determining when you're done with the memory for an object is not always obvious, right? It's easy to forget that you're done with an object, and then it's easy to forget to free it afterwards. Right? So a large part of C programming is ensuring that you are correctly managing memory. That you are correctly managing memory. So to allocate memory, there's three functions: malloc, calloc, and realloc. Malloc gives you back. Malloc is a request for a block of memory. Calloc is a request for a block of memory that also initializes the block of memory to all zeros. Realloc is the function that you call when you have a block of memory and you would like to change its size. Right? When you're done with the memory that's been allocated using any one of these functions, you call free. Right? And so we'll see how to do that in just a second. Okay, so malloc is the function that you use when you want an uninitialized block of memory of some known size. Right? Now remember, in C, all sizes are measured in terms of the size of car. Right? Size of car is 1. Right? All memory sizes are always specified in terms of multiples of the size of. Right? Malloc returns a pointer to the start of that allocated memory block. If for some reason it fails, malloc will return null. We'll come back to this issue here later on. Okay, so I'm going to re-implement makeArray. This time I'm going to use malloc to allocate a chunk of memory large enough to hold n ints. Right, so that's the purpose of this function. Right? Allocate a chunk of memory big enough to hold n ints. Right? So you call malloc, and you tell malloc, how big a chunk of memory do you want? Well, I want a chunk of memory that's big enough to hold n ints. Right? So it's n times size of int. Right? Malloc, on success, returns a pointer to the first element, a pointer to the start of the allocated memory block. You can store that pointer in whatever pointer variable you want. You don't require a cast. Right? If you look at the documentation for malloc, it says it returns a pointer to void, or a void pointer. You can store that in anything you want. So if you want an array of int, then you store it in a pointer to int. right? If you want an array of double, you store it in a pointer to double, and so on and so forth. Once you're done with that, you can return it. So again, our program is just going to ask the user for the size of the array that they want. It's going to make the array by calling our new function here. It's going to print the elements of the array. Right? Notice that we haven't done anything to initialize the elements of the array. Right? When we're done with the array, we're going to free the array. Right? So the only thing we're doing with this array is printing it. So after we're done with it, we're going to free it here. Right? This is unusual. Normally, you don't just make something, do something with it and then immediately free it. Right? Normally, this array will persist for a longer period of time. But it's a small program. So let's see what happens when we run this program. And I'm going to tell you now the output is misleading. Okay, so I'm going to make an array of size 15. And you print out the elements of the array. Notice that the elements of the array, they're not 0. They're not any predictable value. Right? The first element happens to be 0. The second happens to be 0. And then suddenly the elements start, well, it looks like they're going up by 1 every time. Right? So malloc does not initialize the memory that it returns. Right? It allocates some block of memory, hands you back a pointer to that memory. Whatever is sitting in memory is whatever is what you get. Right? So it's very important that you remember the memory is uninitialized. You may have to initialize the memory if you're trying to do something with it. Right? So the output is misleading, as I said. Okay, so the program that I'm actually running is not exactly the same as what's on the slide. So what I'm actually doing is the following. Right? So the program that's on the slide does that, and then it just returns the pointer to the array. What I'm doing instead is I'm asking malloc for a chunk of memory. Then I'm filling in the memory. Right? So I'm filling it in with the values 0 through n minus 1. Right? So I initialize the memory, and then I immediately free that chunk of memory. Right? And then I reallocate the memory. Right? And then I return the array. Normally, you wouldn't do this. Right? So normally, you wouldn't do this. Right? You just allocate the array, return the, ask for memory, return a pointer to the start of the memory block. The reason I'm doing this is to show that the memory that's returned by malloc is, in fact, uninitialized. Right? So that when you run the program here, you actually get something that's not all zeros. Right? If I take out, or if I comment out those, these lines of code, and comment out that second malloc, right? So if I run the program that's shown on the slide, so I'm going to recompile it somewhere, and I'm going to rerun it. Right? You get all zeros. And on a Linux machine, you're always going to get all zeros when you run this program. And that's because of the way that the Linux memory manager works. Right? This isn't, and the problem with this is that if I show you this, you think that, oh, malloc initializes everything to zeros. Right? It's not true. Right? Malloc never initializes the values that are in memory. If you run the code that's on the slide, you might be mistaken, you might be misled into thinking that malloc does, in fact, initialize everything to zeros, right? Because this is the output that you always get if you run this program on a Linux computer. Right? The reason you get this is because when you start up a new program in Linux, the memory manager in Linux wipes out all the memory. So it initializes everything to 0 for you. Right? And so when you run the program, when you run a small program like this, when it allocates memory from that block of memory, it's always going to be all zeros. Right? If you fill in the memory, like I did here, right? So if you actually fill in the memory and then free that block of memory, then what the memory manager appears to do in this case, right, is it appears to return whatever block of memory was returned by the first malloc, right, even though there's a second malloc here. Right? So in other words, once you free that block of memory and then ask for another block of memory, that second block of memory gets allocated on top of the original first one. Right? And that at least appears to be what's happening in this particular program. Right? So the point of all this is to remember malloc does not initialize the memory that it returns to you. Right? And it's very deceptive writing a small program to investigate the behavior of malloc, right? You could be misled into thinking that it returns an initialized block of memory. It does not. Oh, the other way to call malloc, you can specify the size in a different way. If you know you want an array of int, then you might find this to be a little easier to remember, right? So if you know you want an array of int of length n, you can write int square bracket n, and then use size of on that array. And that also gives you back the correct, a block memory that has the correct size. Right, so either that form there or n times size of int. All right, so malloc's pretty straightforward to use. You just have to remember it doesn't initialize the memory. If you want to initialize memory to all zeros, that's what calloc is for. Unfortunately, the way you call calloc is different than the way you call malloc. So calloc attempts to allocate a block of memory for n objects, each having a specified size. Right? So the interface to calloc is different than the one for malloc. It then initializes all the bytes in the allocated block of memory to 0. In other words, it writes a 0 into all the bits of memory. Again, remember that when you specify the size of each individual element, it's always in terms of the size of car. Right? So here's the same function, this time using calloc. Right? So I'm going to attempt to allocate a block of memory big enough for n ints. Right? So you need to specify how many objects you want and the size of each object. Right? Whereas with malloc, you just specify the total size. If you run this program, you will always get all zeros. This should be array calloc, not array malloc, sorry. Okay, so in this case, you will always get all zeros, even if you scribble into memory, free it, and then call calloc again. Right? Calloc always initializes the values. It always initializes the bits in that return memory to 0. Again, you can also do this. This one's weird, though, so I would not recommend you write it this way. Instead of returning enough memory to hold n ints, you can ask for enough memory to hold one array of n ints. Right? I find this one a little bit more confusing to read than this one. Right? But again, it's up to you. They both work. Oh, okay. So that's calloc. And the last memory allocation function is realloc. Okay, so realloc is the function that you call when you have a block of memory that has been already allocated. Right? So you've called malloc or calloc already. You've gotten a block of memory and you decide, hey, I need to make this bigger or smaller. Right? If it's an array, you might be trying to create a larger array, right, that has the same elements as the original array. You might want to make a smaller one too, right, which has the first, which has, again, the same elements as the original array that fit into the new array. Right, so if you have a block of memory that's been previously allocated and you haven't freed it yet, you can call realloc. Right, so realloc takes a pointer to your memory and it takes in the new size, the new total size of the block of memory that you would like. Right, again, in terms of the size of car. Right? Can't be 0, so you're not allowed to reallocate malloc, calloc, or realloc. If you call them with a size of 0, so if you ask for 0 bytes, the behavior is undefined. If it works, you get back a pointer to the new block of memory. Right? So what realloc does? Do I tell you what it does? Yes. No, I don't tell you exactly what it does. Okay, so what realloc does, or what it tries to do, it tries to resize the block of memory that you already have in place, right? So if there's nothing after that block of memory and you're trying to make it bigger, then it will just expand the block of memory that you have, right? If there's something after the block of memory so that the newly allocated block of memory doesn't fit anymore, it has to reallocate a new chunk of memory somewhere and overwrite the contents, and copy the contents over to the, to the new block of memory. right? And so the pointer that it returns, right, it returns a pointer to the new block of memory is not necessarily the same as the pointer that you used originally, right? If it can, then these two pointers will be equal, right? So in other words, if it can successfully reallocate, if it can successfully change the size of the existing block, you get back the same pointer as PTR. If it can't, you get back a different pointer. Right? If it fails, you get back the null pointer. Right? So typically when you're using the allocation functions, you're checking the return value to see if they are null. Right? Or at least that's the recommended advice. I'm going to say more about that in a little bit later. So on failure, it returns the null pointer. Now, if it fails, your original block of memory is not affected, right? So if realloc fails, everything that you had originally is still there, right? So you don't have to worry about that block of memory having been deleted, removed, or overwritten, right? It's still there. If realloc succeeds, then the contents of the original block of memory that fit into the new block of memory is still there, right? So if you have if you're a larger block of memory, all of your original elements are now in the larger block of memory. If you ask for a smaller block of memory, then the first, I don't know, n objects that fit into the smaller block of memory are still there. If the new block of memory is bigger, then any excess memory is not initialized, right? So you have to go in and initialize the new bits of memory that you've gotten from realloc. Okay, so here is make array again using malloc. In this particular case, I'm going to fill in the values of the block of memory. So I'm going to initialize them to 0 to n minus 1. Right? I'm going to ask the user for an array. Right? So it goes through the usual rigmarole, right? Makes an array, prints the array. And then I'm going to ask them for another array a second time. And this time it's going to use realloc to reallocate the memory for the second array. Right? So we'll make an array of size 1. So there's my array of size 1. I'm now going to try to expand the existing array so it has 19 elements in it. Right? And so, right, so there's your original element 0. Right? The new array has size 19, and if you look at the elements here now, you'll notice that there's this funny value sitting here. Right? And so it happens in this particular case that when realloc expanded the size of the memory block, there was something, who knows what, sitting in memory. Right? And now you end up with this funny value there. Right? That's not, that is what you should expect. Right? You have no idea what's going to be in these elements here. Right? Because realloc doesn't do anything special to the memory that it gives you back. Right? So once again, make an array up here. Right? And then I'm going to reallocate the existing array. Right? Not doing anything to fill in the extra values. Right? And to get the new array. If you make the array smaller, that also works. Right? So we'll start out with an array of size 19. Right? Notice that we've got the values 0 through 18 there. And then we'll reduce it to size, well, let's say 4 or 5. Right? And realloc returns that memory back to your operating system. Right? And it leaves whatever values are that fit into the new block unchanged. Right? So malloc, allocate uninitialized memory, calloc, allocate 0 initialized memory, realloc, reallocate an existing block of memory. Oh, notice that in all of the programs, when I'm done with the array, I free the array, right? So you should always free that allocated block of memory. Right? In this particular case, it doesn't matter if you free it, right? Because the program ends on the next line. When your program ends, any of the memory that's used by the program gets returned back to the operating system anyway. Right? So in this particular case, this free is not absolutely necessary. But you should keep in mind that if you're dynamically allocating memory, at some point you probably have to release that memory back to the system by calling free. right? You just call free and then the name and then the pointer to the memory. All right, there's something I need to tell you about, or I should tell you about, this null issue. Somewhere, I think it's in the notebook somewhere. So this is the notebook that's called allocating and deallocating memory. The notebook goes into a lot more detail than I talked about in the slides. Here we go. What to do if a null pointer is returned. All right, so in principle, when you ask for a block of memory, it can fail, right? So at any point of time on your computer, on a modern computer anyway, right, there's a whole bunch of stuff that's currently running in your operating system. So if you look in Windows, if you look in the Windows Task Manager, for example, you'll probably see like 50 or 60 processes running, right? They're all eating up memory and CPU cycles. So you don't have an infinite amount of memory on your computer, right? So if you ask for a block of memory, there's no guarantee that the operating system has memory available to return or to give to malloc, right? So the general advice that's given, so if you look anywhere, if you do a search anywhere on the internet, you'll almost always see the following, right? So if you allocate something using malloc, realloc, or calloc, the very first thing you should do is test if the pointer that's returned is null, right? So in other words, allocate and then test the pointer immediately to make sure it's not null, right? Because if it's null, you didn't successfully allocate the memory, and now you've got a problem, right? The problem that you have is, what on earth do you do now, right? You wanted to allocate memory for something, for a purpose, and you couldn't. So what on earth do you do, right? So if you ask that question on the internet, right, what do I do, right? The answer that you'll get is, well, it depends, right? Because who knows, right? If the reason that you're allocating memory is critical, then your program is probably screwed, right? You probably have to do something to exit the program or shut it down or something, right? If it's not so critical, then maybe you can work around it, right? But no one can give you an exact answer on what to do, right? So the basic line of thought is that if the allocation function has failed, then it's failed because the operating system could not satisfy the memory request, right? There's no memory to give you, right? If the operating system is really out of memory, then there's probably nothing you can do anyway, right? What's happening in the operating system is out of your control. So under such circumstances, the only reasonable thing you can probably do is to exit the program cleanly somehow, right? If you got a bunch of files open, close the files, right? If you got some memory allocated, release the memory, and then shut down the program, right? And you can do that with exit. Right? So the exit function in C will cleanly shut down a program. It will set the exit status of the program to whatever that value is there. Right? So exit 1, or exit failure, sorry, will indicate that will shut down your program and return a non-zero value back to the operating system as the exit status. Right? Whatever that value happens to be is determined by your compiler. Right? You can pass in a different value here if you want to. Right? So you can write exit 9. And it will exit with the exit status of 9. All right, so there's a big blue block here if you're reading the notebooks, right? So this has long been the standard advice given to people who are learning C. Always check the result of malloc, calloc, or realloc for null. The only operating system that's the only major operating system that's used on desktop computers where null might actually be returned is Windows. Right? Every other operating system, so Mac, every version of Linux, will never return null from malloc, calloc, or realloc. Right? So in all other commonly used operating systems, the standard memory allocation functions never return null. Right? If you are in a low memory situation, right, then your program's going to die anyway as soon as you call malloc. Right? So a low memory condition will cause the operating system to terminate one or more memory-intensive processes instead. Right? There's a link if you want to read the research article that explains exactly what's happening here. You don't have to follow that link. if you've got some free time on your hands and this sort of thing interests you, go ahead and hit that link up, and you can learn all about what happens when you, on a modern operating system, when you run out of memory. All right, back to the lecture slide. So any questions on allocating memory? Right? It's really, mechanically, it's really straightforward, right? Call a memory allocation function. When you're done with the memory, return or free the memory, right? In practice, recognizing when you have to free the memory is the difficult part, right? It's very easy to forget to free the memory, and when you do so, you end up with what's called a memory leak, right? You end up holding on to memory that's no longer needed. This is one of the reasons why Java was created, by the way, right? So in Java, the programmer never deals with the destruction of an object, right? The Java virtual machine deals with removing unused objects from memory, right? And this is one of the big motivations for the Java programming language. Right? Sorry, what just happened here? Okay, type def. All right. So this is all leading into this is all leading into us creating new types on our in C, right? So part of creating a new type, is that so you can use this. What is it? It's a statement called type def. So the type def statement lets the programmer declare a new name for an existing type. Right? And so in C, you're going to realize, I guess in a week or so, that some of the type names become very complicated, right? Especially when you're dealing with pointers to functions, right? And so you end up with a type that's very long, and you would like to be able to write that more compactly, right? And so that's what type def is for, right? Type def doesn't make a new type, it just makes a new name, right? The new name is an alias for the existing type, right? So the way you do this is you write type def. That's the type whose name you want to replace. That's the hopefully simpler version of the name. Right? So existing type, new name for the type. Semicolon. Okay, so on my computer, I think I've looked it up, right? We know that there's this type called size_t, right? Remember, that's the size, that's the type that's used to hold the size of objects. Right. On my computer, it turns out that the actual type is long unsigned int. Right? And so the way that size t is defined, if you find the appropriate header file, is that there's a type def. Right? So type def long unsigned int size t says anywhere you write size t, you actually mean the type long unsigned int. Right? You can subtract 2 pointers. I don't think I've told you that yet in the course. So you are allowed to subtract 2 pointers. So the type that holds the difference between 2 pointers is long int. But the language says that there's a type called pointer difference underscore type. Its actual type on my computer happens to be long int, right? So there's a header file somewhere where that line of code exists. Right. So type def is normally used to simplify writing complicated types. Later on, you're going to see that you can use it to do something else as well. Right, so here I'm going to abuse, well, sorry. The first one is an abuse of type def. You should not do this, right? So the first one is I'm going to make my own type. I'm going to create a name called int underscore pointer underscore t, right? So this is a pointer to int. Right? The actual type that it replaces is int star, right? So the new name, int pointer underscore t, replaces int space star, right? So instead of writing int star, I can just write int pointer t. Don't do that, right? If you have a pointer type, a simple pointer type, just use the simple pointer type. Right? The last one is an example of creating a type. Is the example of creating an incomplete new type. Right? So this is the name list, right, is actually a replacement for this thing struct list. So we'll see struct shortly, right? This will actually compile. So nowhere have we actually defined what the actual struct list type is, right? But you can say you are allowed to make a type def to a non-existent type, right? So we say that struct list is an incomplete type because we don't have a definition for it yet, right? And you are allowed to make a type def to a non-existent type, right? Or to an incomplete type. This other thing up here that looks really gross, and it should look gross to you, and it should be impossible to read for most of you, is a type def for a pointer to a function, right? So what this thing is doing is, so it's a bit weird. The syntax is a bit odd. That thing there is your new name, right? So f underscore pointer type is my new name, right? What this thing is, it's a pointer to a function that has two ints as its inputs and returns an int on output, right? And so we'll come back to this later on, right? You don't need to actually, you don't actually have to be able to parse this type def right at this point in time. All right, so here's an example of using a type def, right? So I'm going to use the one I told you not to do, right? So I'm going to use int pointer t, right? That's just a pointer to int, right? So now in my make array function, right? Remember, make array returns a pointer to int. So instead of writing int star, I can write int underscore pointer t, right? Malloc returns a pointer to void. I can store that in an int pointer, right? Instead of writing int star arr, I can write int pointer underscore t instead, right? So it's just a new name for an existing type, in this case, pointer to int. Right? Similarly here, when I call make array, instead of storing the result in a int star in a pointer of type int star, right? I can write int underscore pointer type. All right, so structures. Structures are the C version of are the way that you create what looks like a class in C. Right? So a structure, most people call them structs, consists of what are called members. Members are just variables whose storage is allocated in an ordered sequence. Right? So in other words, a struct is just a group of variables. They're all located in one block of memory having a single name. Right? What it looks like is it sort of looks like a Java class. Right? Now you can't have, there's no methods in C. Right? So it looks like a Java class that has no methods. All of the things in the structure you would consider fields in Java. Right? They're all public, so there's no access modifiers in C either. Right? So what this looks like is you write the keyword struct. You give your structure a name. The name's called a tag. Right? You put in your what look like inside the braces, and then you have a semicolon. Right? So you remember the to class that you probably saw in CISC 124, right? So a point2 object in 124 is just a two-dimensional point, has an x and a y coordinate, right? The C analog of that class is a struct that I'm going to call point2, right? What data does that thing have? Well, it has an x and a y coordinate, and they're both of type double, right? So it basically looks like a class with no methods. Right? The name of the type, right, is struct point2, right? So the name of the type that corresponds to this point always includes the name struct in C, right? So the type here is struct point2, and then you can make an object of that type. So P, right? And that makes one of these objects here, right? The object that gets created has an x and a y coordinate, right? So you don't need new here like you do in Java, right? You don't need a malloc here like instead, right? You just write down struct point2p and you get an object that has an x and a y coordinate, right? What you really get back is a chunk of memory that has room for two doubles in it, right? You can use it right away. So the way that you use the structure is very similar to the way that you use object in Java, right? So if p is right, then I can write p.x, and that gives me the the variable x belonging to the structure. P.y, that gives me the y variable belonging to the structure. Right, so if you print this out, I'm pretty sure it prints 0 and 0. I just have to make sure it's probably in a different directory somewhere. And now I have to find it. So hopefully I can find it. Okay, so it's here. Yeah, so it prints out 0 and 0 in this case. All right, so when you declare a structure, right, you give it a name. The name is called a tag. So the tag name of a structure is not a type, right? So the tag is just a name. Now the interesting thing about tags is that C considers a tag to be different than a variable name or a function name or a type def name, right? So they're separate things. And that means you can have a tag name that's the same as a function name or as a variable name or something else, right? So I can have a tag and a variable that have the same name, right? And so you can think of struct, or not you can think of. So struct followed by the tag name is the name of the type, right? If you don't like writing struct everywhere, you can use a type def, right? So notice back here I had to write struct point 2, right? Oop. It's possible to create a type def point 2, right? That replaces the structure type, right? So struct point 2, that's the actual type, right? I can create an alias for that called point 2, so that is allowed to be the same as that, right? There's no problem because that name is in a different, that name is considered to be separate than that name that you just made here, right? Tag names are considered to be different than all other names in C. So I can just create a type def instead, and now I can write point 2 everywhere. Right? If you search on the internet for advice on using type def, right, some people will say this is useful to do. Other people will say you should never do this, right? So in other words, there's a fairly vocal group of people that say there's no advantage to doing this, right? By writing point 2 here, you don't actually, this hides the actual type of P, right? You don't know what it is anymore, right? Whereas if you write struct point 2, you know that it's always a structure, right? So Linus, the guy who created the Linux programming, the Linux operating system kernel, he says you should never do this. I'll leave it up to you to decide what exactly it is you want to do. Okay, so when you make a structure, right, when you create a structure object, generally you have one or more variables inside the structure. Normally you want to initialize those values, right, when you create the object. So you can initialize them in the same way that you initialize an array, right? You can write the squiggly brackets and then put in the values inside the squiggly brackets, right? So for example, right, point 2p. So I'm going to use a type def here to save me writing struct point 2 everywhere, right? So point 2p equals 2 and 3, right? And so that takes the value 2 and assigns it to x. That takes the value 3 and assigns it to y, right? So that makes the point 2, 3. Right? If you want to be explicit in which members you are initializing, you can use dot something, right? So dot x equals 1 sets the x value, the x member to 1. Dot y equals 1.5 sets the y member to 1.5. Right? You don't have to initialize all the members, right? So if I write dot y equals minus 3.1, that creates a point whose x coordinate is 0 and whose y coordinate is minus 3.1. Members that are not explicitly initialized get initialized to 0, right? So 0 initialized for a pointer means that the pointers are null, right? So if your structure has a pointer type inside of it, right? So imagine my point 2 type has I don't know, an int pointer inside of it, right? If you don't initialize the pointer, that pointer gets initialized to null. Accessing members. Okay, so access the members of a structure, you can use dot. Now, that changes if you have a pointer to a structure object. Okay. So if you have a pointer to a structure object and you want to access the member via the pointer, you use hyphen greater than, so it looks like an arrow. Right? What that does is it dereferences the pointer to the structure and then accesses the member directly. So there's P, right? It's a plain old, it's just a regular struct object, right? Its values are 2 and 3. So to get to x and y, I just write px and py. Right? PTR is a pointer to a point2 object, right? So now it's a pointer. If I want to get to the x member of the object pointed at by PTR, right? I can write arrow, hyphen greater than x, right? That dereferences the pointer and then accesses the x member. So now I can set that to 200, right? PTR hyphen greater than y dereferences PTR, gives me and accesses the y member to be 300. Is there? I should show you the alternate way to do this. Okay, so remember PTR is a pointer, so I can always explicitly dereference the pointer. Right? So if I dereference the pointer, in this case it gives me back the object P, right? So now I can write P dot x. Right? And similarly here, right, I can explicitly dereference the pointer and then use dot y to get to the y coordinate. Right? So that is just short form for this. Right? If you want to, you can forget about this notation and just dereference the pointer whenever you need to. Right? But it's generally more convenient to use the arrow operator in this case. Right? Okay, so in C, you can assign one struct object. You can assign struct objects to one another. Right? What ends up happening is you end up copying members of each structure. You end up copying the members of the structure to the other structure. Right? If the structure contains a pointer, then you have two struct objects with a pointer that points at the same object. So you have to be a little bit careful when your structures have pointers. Right? This is different than in Java. Right? So in Java, if you have two strings, right? So in Java, string s equals something. Right, and then string t equals s, right? That does not make a copy, right, of the string s, right? You've now got two references to the same string. In C, it's different, right? So in C, if you have two structures and you do an assignment, then you actually get a copy of that of the assigned object. Right, so here's P. It's 2, 3. Here's Q, right? Q is uninitialized, so its members get initialized to 0. So that's 0, 0. If you write Q equals P, right, that takes the 2, the x belonging to P, and copies it into the x belonging to Q. Right? It takes the y belonging to P, copies it into the y belonging to Q. So when you print out Qx and Qy, right, you end up with 2, 3. If you change Qx and Qy, right, to 200 and 300, and then print out P and Q, right, P is still 2, 3, so it's actually a separate struct, right, it's actually a separate object, and then Q is 200 and 300, right, it's actually separate from P. Right, so the way that structures behave are, so I told you that structures are basically, they resemble Java classes, right, they behave differently under assignment than in Java. You can dynamically allocate memory for a structure or an array of structures, right? When you dynamically allocate memory for a structure, you need to know how big is the structure. You just use size of to get the structure size. right? So if I want to allocate space for one 0.2 object, I can just write size of 0.2, right? And then I can store that result in P, right? Now remember what this does, right? Malloc allocates enough memory for one 0.2 object. It does not initialize the memory for that object, right? So if you try to access the fields px and py via the pointer, right, you don't know what's sitting in px and py, right? It could be anything, right? Because malloc does no initialization, right? So here I'm going to explicitly set px and py to 100 and 200, and then when you print them out, you'll get 100 and 200. Right? You can allocate an array of pointers too, right? An array of 0.2 objects as well, right? You just malloc n times size of 0.2. That'll give you enough memory for n 0.2 objects. If you want to compare two structures for equality, you're kind of stuck, right? You cannot use equals equals or not equals to determine struct equality, right? They don't exist. So the operators are not defined for structures. If you try to do it, the compiler won't compile your code. Right? So if you need to compare two structures for equality, then you have to decide what does it mean for your two struct objects to be equal, and then you have to write a function. Right? Well, you probably have to write a function, right? If you're going to do this over and over and over again. Right? So I have P, its coordinates are 100 and 200. Right? I have Q, it has the same coordinates as the object pointed at by P. If I want to check is P equal to Q, right, I have to write my own code to do so. Right? So if you decide 2 points are equal if their coordinates are equal, now I have to go in, get the coordinates of whatever P points at, get the coordinates for Q, and compare them. Right? P is a pointer, so I have to dereference the pointer or use the arrow notation. Right? Get the x coordinate, test if it's equal to qx. Right? P is a pointer. I have to dereference the pointer to get the y coordinate, test if it's equal to the y coordinate of q. If they're the same, then we know that they're equal. Right? So if you want equality for your structures, you probably want to write a function that can determine equality for you. Right? All right. This is a good place to stop. So what we're going to go, so the next step in the course, right, is to use structures and dynamic memory application to actually implement a meaningful data structure in C. All right, so the next thing we're going to do is we're going to implement a list, I think, in C. All right.
Are we going to get a practice test?
Yeah, I'll post something about the quiz this afternoon. Yeah.
It's just bash.
It's bash and a tiny bit of C.